Hi, my name is Kazi Hamza Jan and I am doing my PhD in Robotic Research Lab, RPTU, Kaiserslautern Landau. My topic is navigation of autonomous vehicles in pedestrian zones. Mainly I'm working with this project called Autobus. This Autobus is meant to drive in pedestrian zones such as campus environments, city centers, airports, where we have pedestrians around, where there is no special marking, separate marking or segregation for the pedestrians. This vehicle differs from the rest of the existing vehicles, because it has this special interaction modules. So the idea is that we interact with the pedestrians for priority to make them aware of the vehicle and avoid such kind of collisions.
Please give way.
Other than this, this vehicle is also equipped with special safety certified system. This system was bought from SICK and they specialize in these kind of safety modules. The basic vehicle was bought from Compai, which is based in France. They work in collaboration with Technical Studio, and they offered this basic control to motors and brakes. And then we built this vehicle by adding all the different sensors, the electronics and DC to DC converters, and of course the safety system. The vehicle consists of different sensor systems such as 3D laser scanners, 2D laser scanners and stereo cameras. The point cloud is used to perceive the environment and understand the obstacles, and the images are used for segmentation to find the drivable area. So as I already mentioned, that we have different concept for this vehicle. So first of all, the first concept is pedestrian interaction framework. What this does is this detects the pedestrian, tries to figure out the posture and behaviors of and intentions of the pedestrians, and based on that then we can interact with different interaction modules such as LED display, voice or lights. Then the next concept is to have an interactive navigation. By interactive navigation I mean is to have based on the intentions of the pedestrian, we navigate accordingly. So it's not just perceived as some random dynamic obstacles, but we communicate with them through these interactive modules, and then based on their reaction we can navigate accordingly. So for example, if someone wants to perpendicularly cross the vehicle in front and we want to have our priority, we give a signal through the display that not to cross, and if the person, based on that reaction, if the person stops, then only we can cross, otherwise we really need to slow down. And then the third concept is socially influenced decision making. So this is almost related to navigation, that unlike conventional driving, it not only depends on the steering and velocity control of the vehicle, but also it controls the interacting modules along with the velocity and steering. So they both work simultaneously. So the last concept is the hardware safety. So the hardware safety is independent of the navigation algorithms or higher level algorithms, and it is directly connected to the safety chain of the vehicle. So once someone comes in the safety fields of the vehicle enables the emergency brake and it suddenly stops, and it has to stop. So this kind of hardware safety is important for some kind of special or specific behavior, such as if a child jumps in front of the vehicle, or failure in detecting the people. In that case the vehicle has to stop. So these are some concepts which really differentiates this vehicle from the rest of the state of the art. So coming to the sensor configuration of the vehicle, we have 6 stereo cameras mounted on the roof of the vehicle and 2 3D outer scanners. The idea of 3D laser scanners is to map the whole environment, and the main idea of using the stereo cameras is to detect the skeletons of the pedestrians, and based on that further reckon the activities and intentions of the pedestrians. This range of the stereo cameras is around 15 meters, which is sufficient for such kind of vehicle, because this vehicle will drive maximum 6 km per hour in a pedestrian zone. It is not allowed to drive more than a walking speed. When we look at the hardware configuration, since there are so many sensors on the bus and we are getting so much data, so we need to distribute this processing part. For this case, we have 3 Jetson boards on the roof of the vehicle where 2 stereo cameras are attached to each Jetson. The purpose of using these Jetsons is that we do the skeleton detection on these Jetsons, and then further this data is then transferred to the main PC through switch. So we have a switch on the roof where all these sensors are then connected. Furthermore, we have 2 embedded PCs in which the whole existing navigation system which we have, which we call reaction, is distributed. The modules are distributed between these 2 embedded PCs. So for the navigation, we have 3 different strategies of navigation which are later fused in the framework. The first strategy is based on tentacles. So we have aspect maps which identifies the drivable region and the obstacles, and based on that the tentacles then get their weight. Then we have also done end-to-end driving on this vehicle, where we directly take the images from the front camera and then steer the vehicle. And also we tried deep reinforcement learning, but this was only done in the simulation at the moment. So as mentioned earlier, that we have this pedestrian interaction framework. This includes understanding the behavior and intentions of the pedestrian. So we have used 2 approaches to do this. The first approach is using LSTMs. In this approach, we use 3D skeleton points in number of frames, and then we try to understand the behavior of the person. But what is different here is that we divided this activities into 2 different categories. One is the primary activity and one is the dynamic activity. So the lower half of the person, which means legs, these are the primary activities, which includes the crossing or standing behavior. The upper half of the person above the waist, these includes the secondary activities, which includes the calling or texting or doing nothing. So one approach was LSTM and the other approach was a geometric approach, where we have these different we have 3D skeleton joint points, and we find the angles between these points, and after fusing these different angle from the body parts, we get a posture of the person. So we know what kind of posture, is it walking, is it standing, is it sitting, so we can get all these postures. In conclusion, we saw that adding the interaction framework really helped to drive safely through the campus environment, because this generates trust between the vehicle and the pedestrians, and pedestrians or people, they feel more relaxed around the bus. Also, time was reduced by not having unnecessary stops, and the passengers were also content with the drive. So this is all about the Autobus, and please visit our lab to have this experience. Thank you.